Hey, future data scientists! Welcome to your ultimate guide for acing data science interviews. Whether you're a fresh graduate, career switcher, or seasoned pro, this video series is your secret weapon. Let's crack one of Amazon's most asked data science-based questions.
How does random forest handle missing values? It is always good to ask some question around why the data is the missing data is there in the first place. This shows your curiosity as a data scientist. Missing values can be due to informative, example, a customer didn't respond to a survey, or due to a data quality issue. Use a separate category to represent missing values if it is informative. If it is due to data quality, following imputation methods can be used: listwise deletion, simple methods, mean, median, mode, advanced methods, k-nearest neighbors imputation, multiple imputation by chained equations. Important: use advanced methods if only needed. It will decrease the interpretability of the data. How does tree depth affect overfitting in random forests? In a single decision tree, increasing depth almost always leads to overfitting because the model can keep splitting until each leaf captures very specific training patterns, even noise. But in a random forest, the ensemble context changes things. Each tree is trained on a bootstrapped sample and sees a random subset of features at each split. Because of this randomness, the overfitting behavior of one tree is averaged out by many others. So even if each tree overfits slightly due to high depth, the forest as a whole can still generalize well, because it captures a wide range of signals while smoothing out noise through aggregation. Deeper trees in a random forest often improve performance up to a point because they allow the model to fully leverage complex interactions in the data. In fact, limiting depth too aggressively can underfit the ensemble, especially in high-dimensional or nonlinear problems. That said, if trees are too deep and the number of estimators is low, or if the data set is small, variance can creep back in. So depth needs to be tuned with respect to the size of the data, number of trees, and overall diversity in the forest, not just treated as a standalone hyperparameter like in a single tree setting.
Why does increasing the number of trees in a random forest typically reduce variance but not bias? Under what circumstances could adding more trees harm model performance? Variance reduction. More trees leads to more averaging, which leads to lower variance in predictions. Bias. Each tree is a high bias estimator, shallow, random splits. Averaging does not reduce bias, only variance. When more trees hurt, extreme memory or computation constraints can slow down training or prediction. If data is noisy or has data leakage, more trees may amplify overfitting to noise. How do you decide between random forests or gradient-boosted trees? Random forests are primarily variance reduction machines. It averages many deep, high-variance decision trees trained on bootstrap data and random feature subsets, which reduces overfitting through decorrelation. Its bias is relatively high if the underlying structure is complex. GB trees are better for reducing bias by fitting complex, nuanced patterns. A new tree of GB builds on the mistakes of the last. The model becomes highly sensitive to noise and requires careful tuning to avoid overfitting. So while bias is often lower, variance can be higher. Use random forests when data is noisy or when robustness or minimal tuning is a priority. You're dealing with a large data set and want to parallelize. You want quick, reliable results with minimal tuning. Training speed matters more than absolute performance. Use gradient boosting, example XGB, LGBM, or CAT boost when the dataset is not noisy and we need state-of-the-art accuracy, particularly in structured data problems like credit scoring or ranking.
You're okay with slower training and hyperparameter tuning. You want state-of-the-art performance. You need to handle imbalanced data, complex interactions, or small datasets. How does the presence of highly correlated features affect feature importance in a random forest, and why can this be misleading? Random forests can split on any of several correlated features, so the importance gets divided among them. This means each correlated feature may look less important than it actually is. As a result, feature importance rankings can be misleading when features are highly correlated. It's a good idea to check for multicollinearity and consider dimensionality reduction or alternative importance metrics like SHAP in these cases. Explain how out-of-bag error is calculated in random forests and discuss its advantages and limitations compared to traditional cross-validation. Out-of-bag error comes from using the data points not included in each tree's bootstrap sample to test that tree. It's an efficient way to estimate generalization error without needing a separate validation set. Out-of-bag error is quick and built-in, but can be unreliable with small or highly imbalanced datasets. Cross-validation is more robust for hyperparameter tuning, but out-of-bag is a great free estimate for large balanced datasets.
Thanks for watching. If you found this helpful, subscribe for more data science and machine learning content to ace your career journey. Hit that notification bell so you never miss a video.